sometimes we could find a power series by differentiating or integrating to get that power series. That's what this video is all about. This is the second video of the power series lesson, which is still the second part of the first lesson in the unit. Let's get going. Just two examples here for you, and the first one is finding a power series by differentiation. We're about to find a power series for this function, and I just want to remind you what we're actually doing here. We are using a collection of terms in infinite series to represent a function. Not necessarily any function, but specific functions, and there are some major ones that we've studied in the past. Now this one doesn't really come to my mind as a famous function that we would study, but some of the mathematicians that came before us might think otherwise. What I mean by that is this function is a little bit more common to us than we realize. Let me show you. So let's say we took the derivative of 1 over 1 minus x. Now I just didn't pull that out of thin air. I realized that whenever we have a function, a rational function that has a power in the denominator, maybe it was the derivative of some other function. So this derivative is the same as if we were to take the derivative of 1 minus x to the negative 1. Again, I know what you might be thinking, that's not even a common function that we took the derivative of either, but x to the negative 1 was. And the 1 minus x is special here because of the interval of convergence that we're kind of thinking about and trying to see on a graph. And the derivative of this using the power rule and the chain rule looks something like this. Now at this point, this is the power rule. We multiply by the negative 1, decrease the power by 1, and then the chain rule says multiply by negative 1. And if I multiply those negative 1's together, I get a positive 1 that's over 1 minus x to the 2, which is the same as what we started with. So I didn't look it up, but I wouldn't put it past Leonhard Euler to be the one who would have studied a function like this. You know, he was interested in not the most glamorous types of functions, more ones like natural log and rational functions. Okay. Now that we know that this function is the derivative of 1 over 1 minus x, let's start with what is 1 over 1 minus x as a series, as terms. All right, well the first term of that series is 1, followed by x, and r is x. So again, the sum of that series, a in the numerator, and this is the r value when it's in that form. So x squared, x cubed, and so on, all the way up to x to the n. And what we're about to do here is called term by term differentiation, meaning we're just taking the derivative of this series, and that looks like this: 0 plus 1 plus 2x to the 1 plus 3x squared plus so on and so forth, all the way up to, and this is a key part to this step. If we didn't write this, this would be a waste of time. I mean, it's already starting to look like that way sometimes, like why are we even doing this? And this last term is the general term. Great, so if we call that the general term, well, how are we writing the actual power series? To go back to the original setup or question, we're finding a power series. So what is that power series? Well, this is the power series right here. A series is a sum of terms. If we want to write that in Riemann sum notation, we can do that. We could say that n equals 0, and it goes up to infinity of n times x to the n minus 1. Let's double check that. When n equals 0, then we're going to plug that into this expression here. So n equals 0, x to the negative 1. Well, whatever that is, it's being multiplied by 0. That's that term. Let's try 1. N equals 1. That would be 1 times x to the 0, which is 1. There's our 1. And let's just check one more to be sure. Plugging in 2, we get 2 times x to the 1. Aha! That's what this is. And we keep doing that and we'll get all of the terms. All right, well that's term by term differentiation. Let's take a look at what term by term integration would look like. Not too much different, but a little bit of challenge maybe with notation. And before I show you how to find a power series for natural log of 1 plus x, which again would be like something Leonard Euler would do, I just want to point out I don't think this is a major concept in this unit. We're about to get there. Really the first part of this lesson was a major piece of what we're doing, is writing out partial sums and analyzing the graph. Nonetheless, let's take a look at this and see how we could do this, because really the process is fairly simple and the College Board might request students to do this every so often. And here we go. What we could do is we could say the derivative of natural log of 1 plus x is equal to 1 over 1 plus x. And that, my friends, that is some expression, that's a function that we're getting somewhat familiar with already based on an exploration in this very topic, but also thinking about the sum of a geometric series, again in that form of a over 1 minus r. So we could rewrite this to be 1 minus negative x. And let's just write out these terms and integrate. And, oh, hey, okay, sorry about that. So what we're going to do, write out the terms and integrate. So that means 1 over 1 plus x. Well, that's equal to this. Okay, the terms are alternating because the r is negative. So we really have negative x to the 1 and negative x squared, which is positive x squared, and so on. That nth term is negative x to the n, and this is on the interval from negative 1 to x, or, from negative 1 to 1. And that's based on the geometric series stuff we learned before. Now, if we integrate from 0 to x of 1 over 1 plus t, all right, a little side note is that I'm choosing a t to let this vary basically. Not a huge deal here. I could say 0 to t of 1 over 1 plus x, but that's a dummy variable. So we're writing them in terms of t, and that means term by term integration of this right here. Sorry, of these terms right here. So the antiderivative of 1 is t. The antiderivative of x is t squared over 2. Thinking, wait a second, why did the x just turn to a t? And that's because now we have to think about all of these terms as t's. No big deal, just stick with me here. The next one would be x cubed over 3, and then negative, oh my goodness, I did it. I knew I would do it. I knew I'd do it. Negative t cubed over 3, and minus t to the 4th over 4. And the series goes on forever. And it's alternating. So we have a negative 1 raised to the n power. We have a t raised to the n plus 1th power, which is basically the reverse power rule. And we have an n plus 1 in the denominator, which is part of the power rule as well. And we're integrating that from 0 to x. Oh my goodness, are you still with me? You can do it. We took the antiderivative of each term using t's, integrating from 0 to x so that we get the actual terms as x values. Why did I do that? Oh my gosh, I could have just wrote them as x's, but I'm trying to follow the rules for you that if we were to take the integral from 0 to t of 1 over 1 plus t, that would just be one number. It doesn't vary. All right. That means we have found our general term that we could have written, or we could write as a Riemann sum. Oh my gosh. That's an x. a Riemann sum from 0 to infinity of this general term. In conclusion, I think one thing that I learned from going through this process, starting from the first time I encountered these processes, what the mathematicians were thinking about when they were curious about these series, but also, how the chain rule, how the power rule come into play in processes like these, and how to connect various functions. Seeing that natural log of 1 plus x is connected to 1 over 1 plus x in this way. It's pretty unique. All right, thanks for sticking with me on differentiating and integrating power series. I think you'll really enjoy the next topic about Taylor series, which is really one of the biggest concepts in the unit. Alrighty, bye-bye.